So welcome to the second session on centrifugal compressor. Now we will try to find out an expression for the pressure ratio. For that we may consider two of the equations. The first one is the energy per unit mass, which we have already derived in the first session. It is equal to Cp into T03 minus T01, which is equal to psi sigma U2 square. Two expressions for the work done. And as the process inside the compressor can be considered as an adiabatic or isentropic process, we can use the adiabatic equation of pressure ratio P03 by P01 is equal to T03 dash by T3 by T1 all raised to gamma by gamma minus 1. These two equations are important. So consider a temperature entropy diagram. Let the two isobaric processes are represented as P01 and P03. P01 is the pressure at the inlet of the compressor. P03 is the pressure at the outlet of the compressor. So the process from inside the compressor is considered to be isentropic. That means it will be represented by a vertical line from 1 to 3 dash. Let it be 3 dash. This is an ideal process, a theoretical process. But the actual process will not be isentropic. It will be an adiabatic process. It will be like this. So let that point be 3. So applying the pressure ratio P0 by P01, P03 by P01, it will be equal to T03 dash by T01 all raised to gamma by gamma minus 1 for this theoretical adiabatic process, isentropic process. Okay. So because there is an ideal work done and an actual work done, there is a ratio known as isentropic efficiency eta C, which is given by ideal work done by actual work done. Ideal work done is the work done for this ideal process, and actual work done is the work done for process 1 to 3. So it will be equal to Cp into, we have derived it, that work done. This is the formula for work done, and that will be equal to, for ideal process it will be Cp T03 dash minus T01 by actual work done is Cp into T03 minus T01. So what will be eta C into T03 minus T01 will be equal to T03 dash minus T01. So dividing by T01, we will get it as T03 by T01 minus 1. So that means T03 dash by T01 will be equal to, this 1 will come here. So 1 plus eta C into T03 minus T01 by T01. Now apply this equation, T03 by T01, apply this equation. P0 by P01, P03 by P01 is equal to T03 dash by T01 all raised to gamma by gamma minus 1. So applying that here, it will be from 2, from this equation, it will be substitute for this one, P0 by P01, P03 by P01 will be this term, the all raised to gamma by gamma minus 1, gamma by gamma minus 1. This term all raised to gamma by gamma minus 1. Now consider this term T03 minus T01. Here it is there, T03 by T01. It is equal to psi sigma U2 square. So Cp will be coming into this side. T03 minus T01 will be equal to psi sigma U2 square by Cp. So substituting here, P03 by P01 is equal to 1 plus eta C psi sigma U2 square by Cp divided by T01 the all raised to gamma by gamma minus 1. This is a very important equation, which is the pressure ratio, expression for pressure ratio of a centrifugal compressor in terms of isentropic efficiency, the power factor, the slip factor, the stagnation temperature at the inlet, and the peripheral velocity of the impeller at outlet. With a little consideration, you can see that eta C, psi, sigma, Cp, T01 all are constant. So this is an expression for the pressure ratio of the compressor in terms of U2 square. That's very important. Now we will move on to another important topic known as the characteristic curve of a compressor. Characteristic curve of a compressor, and with that we will explain two phenomena known as surging and choking. Surging and choking. So this is a graph plotted with pressure ratio and mass flow rate. This is a curve plotted for the operating speed. We can have similar curves for different operating speeds. And if you analyze, you can see some key points. The first point is A, and another point is B here, another point is C here, and another one is D, and we will explain a point Q also. So let us consider a compressor here. This is the impeller, this is the diffuser, together it will be a compressor, and there is a delivery valve here, and this is the downstream end of the compressor, and this is the delivery end of the compressor. You can see that the part AB has a positive slope, the part BC has got a negative slope, with B as the maximum pressure ratio, which will be the maximum efficiency point for the compressor. So when the mass flow rate is 0, you can see here, when the delivery is completely closed, the mass flow rate will be 0. Then again, the pressure ratio is not 0 or 1. It is having a value at A. That is because even if the delivery is closed, even if there is no flow in the diffuser, the impeller is rotating and it is churning, and this churning action causes the centrifugal head, and there will be a pressure ratio, and that pressure ratio is indicated by the point A. So it is not 0 when the mass flow rate is 0. Now consider that the delivery valve is opened. That means the mass flow rate is increasing. So the delivery valve is opened and the mass flow rate is increasing from A. That means the flow starts through the diffuser, and the diffuser also will act on its quota of increasing static pressure. That's why the pressure ratio is increasing. But at a point B, for a particular position of the delivery valve, the point B is reached where the pressure ratio will be maximum, and from there, when the delivery is more opened, when the mass flow rate is increased, the pressure ratio is keeping on decreasing. This is because beyond the point B, the pressure ratio is actually compensated to overcome the frictional losses so as to maintain a high mass flow rate. That means as the mass flow rate increases, the frictional losses also increases, and the pressure ratio is being utilized to overcome this frictional losses. That's why the pressure ratio is keep on decreasing, and theoretically the mass flow rate will be 0 at point C. It is only a theoretical point. We will come to that. Now we will consider our discussion on the part AB. This AB part is known as an unstable part. Consider an operating point Q on AB part, the positive slope part. Consider the point Q here. The compressor is operating at the point Q. It has achieved a steady state and it is delivering air. But with a small disturbance, for example, if we close the delivery valve for a little bit, that means when the mass flow rate decreases, the pressure ratio, you can see the pressure ratio, when the mass flow rate decreases from this point Q, the pressure ratio decreases rapidly. That means at a point between A and B, for example at Q, when the mass flow rate decreases a very little, that means with a small disturbance in the flow or with a small closure of the delivery valve, when the mass flow rate decreases, the pressure ratio decreases drastically, rapidly. That means the pressure ratio will be decreasing at the delivery end rapidly. But this rapid reduction in pressure will not happen in the downstream end. So what happens is that the pressure in the downstream end will be more than the pressure in the delivery end after some instance. So this will cause a reversal of flow from the downstream end to the delivery end. And this will obstruct the flow from the delivery end further. That will cause the pressure to drop further. So the flow will happen more flow will happen from the downstream end to the delivery end. But as the flow proceeds, the pressure in the delivery side decreases and it keeps on decreasing up to the point A. By this time, as there is no flow to the downstream end, the pressure start to decrease here. And as time proceeds, the pressure will keep on reducing such that it will be lower than the delivery end at the point A. It will be lower than at point A. So at this time, the pressure in the delivery end will be more than that in the downstream end. So again, flow will start from the delivery end to the downstream end. So this phenomenon of instability with a slight reduction in the mass flow rate in the region AB can cause a flow reversal, and this phenomenon is known as surging. Okay, so this surging will happen on all the points below a certain level from B to up to A. But if you consider a point here, for example at D, if you consider an operating point at D, and if you reduce the mass flow rate, what happens? If you reduce the mass flow rate, the pressure ratio is increasing. So there is no point of flow reversing from downstream to delivery end, because the pressure always will be more in the delivery end. So the flow will not reverse from the downstream end to the delivery end in any of the operating points here beyond B to the right. So that is a stable region. But as we have already discussed, the mass flow rate cannot be zero theoretically at point C. Even before C, at a particular point around D, what happens? As the valve is being opened and the mass flow rate is being increased from B. As the mass flow rate is increasing, the velocity of flow keeps on increasing. At a point around D, depending on the operating speed of the compressor, the velocity of flow will reach the sonic level. So if the velocity reaches the sonic level, the mass flow rate cannot be further increased by adjusting the delivery valve. This point where the velocity of flow reaching a sonic level is known as the choking level. So D represents the choking point, and the mass flow rate corresponding to point D will be the maximum mass flow rate possible. It will not be C. C is only a theoretical point. So that is about surging and choking, two important phenomena. Very important. Now we will move on to another topic known as degree of reaction. What is degree of reaction? We have considered this term in centrifugal pump also. So degree of reaction is actually the ratio of static pressure rise in the impeller divided by total static pressure rise in the compressor. That means it gives the quota of contribution by the impeller to the static pressure rise given by the compressor. So it is static pressure rise in the impeller divided by total static pressure in the compressor. And what will be the static pressure rise in the impeller? It will be equal to the change in kinetic energy provided by the impeller, and from the Euler's equation it will be equal to VR1 square minus VR2 square by 2 plus U2 square minus U1 square by 2. What is VR1 square minus VR2 square by 2? It is the pressure rise in the impeller, the static pressure rise in the impeller due to diffuser action. As the air passes through the passages of the impeller passages are divergent, and because of this diverging passages, the diffuser action of the impeller causes to rise the static pressure. That component is VR1 square minus VR2 square by 2. And what is U2 square minus U1 square by 2? This is the component by which the static pressure is made to rise because of the centrifugal action. So the centrifugal, as the impeller is rotating, when the air passes through the impeller, there will be a centrifugal head imparted. And by the introduction of centrifugal head, the static pressure will rise. And that component is U2 square minus U1 square by 2. So together, the diffuser action and the centrifugal action, both done by the impeller, will cause the static pressure rise in the impeller. So that will be the numerator part. The static pressure rise in the impeller is because of the diffuser action and by the centrifugal action. These are the two terms. And what will be the total pressure rise in the compressor? It is the actual work done by the compressor. Work done by the compressor, we have found it as Euler's equation is VW2U2, the simple equation VW2U2. So degree of reaction will be this component in the numerator divided by VW2U2. And if we can find out the terms and analyze this equation using the inlet and outlet velocity triangle, you can simplify that the degree of reaction as 1 minus VW2 by 2U2. So degree of reaction, which is actually is the measure of the contribution of the impeller to the overall static pressure rise in the compressor. Degree of reaction is equal to 1 minus VW2 by 2U2. So that completes the theoretical topic of the centrifugal compressor. Thank you.